Okay, so we will be talking about a special topic today on which quantum mechanics is governed, in which is known as actually it has two forms. One is h and one is h bar. H stands for Planck's constant, and the second one is reduced Planck's constant. Re sorry, reduced Planck's constant. So to go from Planck's constant, sorry, h to h bar, what we do is that we do h divided by 2 pi. We divide it with 2 pi and we get h bar, the equation you can say. Well, we just divide with that equation where pi, uh, 2 pi. Okay. Now, uh, by the way, do you know from where this 2 pi actually came from? I'm not sure, but when we talk about, okay, we'll talk about it in in a while, because we will cover one extra topic, which is sorry angular momentum, but in terms of quantum mechanics. Okay, so first of all, let's cover these two topics, h bar and h. So the equations which include h and h bar, even this also includes h bar, are E is equals to h frequency. This is frequency, and this is h bar as we have. This is energy, and then we have E is equals to h bar h, this E of h v over k b t minus 1, and we all know the equation which is this. We all know this equation which is regarding the energy, discrete energy. Okay, over here this equation is related to radiation, black body radiation, black sorry body radiation. Okay, now, and then we have equation which what was, yeah, de Broglie equation. De Broglie wavelength. Okay, now again, h by h and h, all these. By the way, what h really is that h is showing the discrete property of energy, discreteness is being described in, is discreteness a word? Yeah, discrete, that energy levels have to be discrete, and this equation can be rearranged in h is equals to h e over frequency, that h is the energy of a particle associated with the frequency, and so the value for h is 6.6, sorry 6.626 times 10 to the power minus 34 joules per second, which can also be written as 6.2 sorry 626 times 10 to the power minus 34. We know that joules is nothing but Newton meter, and Newton meter is nothing but kilogram meter square dot And Newton meter is what? Newton meter, and Newton meter can be written as kilogram meter per second square dot meter dot dot second. So it gives us kilogram meter cube square s1. This is the base unit. So, and this is reduced, one is 1.055 times 10 to the power minus 34. And so then, uh, yeah. So what else we have in this topic, that h bar or an h is that so blackbody radiation is this blackbody radiation. And yeah, one more equation I forgot, which is this equation, the Heisenberg uncertainty principle. Okay, Heisenberg uncertainty principle is also one of the famous ones. Okay, and Planck's constant in this governs uncertainty principle, which sets limit on how precisely we can measure pairs. By how precisely we can measure pairs, that measuring one pair, one of the properties affects the other one. That's why this over here sets a limit. H is acting as a limit. Complementary properties of position, axis position, and p is momentum. And this over here, this one is governing the wave particle property of light or particles. And here this, okay, the equation itself is showing what we are talking about, the relationship between photon and photon's energy and frequency relationship. It's not only photon, it can be other particles as well, but it's taken as photon's energy associated with its frequency. So because all of this, the word h is his this word, this h, Planck's constant, is based on Max Planck. Okay, so then um, these are where h bar and h are used. And so we can say h limits the scale. H is actually is actually showing the range or scale scale level scale level. Because when we look at the value, uh, 6.626 times 10 to the power minus 34 joule second, this minus 34 is extremely small. Okay, because Planck's also, then there's Planck's length. So Planck's length can also be one of the factors in which Planck's constant is there. Again, Planck's length does have Planck's constant. Sorry. Look, smallest scale in physics, below which classical concepts of space and time break down. Yeah, that's okay. That's good definition. Smallest scale in physics, after which classical physics will not work due to quantum gravitational effect. And actually, guess what? It has a formula as well, which is square root of h bar g c cube over c cube. Okay, where we know that c cube and g are also constants like h bar and h. That what was it again? The one g is known as gravitational constant and c is known as uh, what was c again? Speed of light. And so it sets a theoretical limit below which current physics cannot describe a phenomena directly. By current physics, I mean classical physics. Okay, so now that we have like covered h bar and h in many equations, and so we will now talk about angular momentum, in which h bar again is included, of course, because it's also part of that. Now, what is angular momentum in terms of quantum mechanics is in terms of angular momentum, h bar is known as angular momentum is known as in terms of quantum mechanics is that, let's suppose we have a nucleus. Sorry, nucleus. I no, I don't think so. That's correct. Okay, fine. Proton, neutron. Sorry, I'm like sick a little bit. So after that, and it has we know that it has electrons around it. Now, and one more diagram should be made. Now, wherever you see the waves, it's showing the wave nature of electron, and this over here is showing the um, particle nature, if I'm right. So we know that in by through de Broglie equation that wavelength is equals to h over p, which is momentum. We know the momentum is associated with wave. That when we know when we know it's in the wave nature, what we are looking at is its momentum. Okay, so and then so that means we know that momentum is mass times velocity, and since electrons also have mass, they move, so they can have momentum. So we could rewrite this equation as lambda is equal to h over mv. Now, um, one more thing over here, if we notice, did you notice something here, that if I start from here at this point and move around the whole circle, I return to the same point, which is what is it? It's the circumference. 2 pi r is the circumference. Okay. So what we could write is we could rewrite this equation in terms of circumference. Okay, so we could write it as wait, show me. R is equal to R times P. This is in terms of classical physics. classical physics. Okay, and we will end up with the same equation that what we will do is we in here we know that the with 2 pi r is equal to h over mv, and so we could take it as now we replace this equation over here. We will replace this 2 pi with a mv. So what I get is uh, what we get is m sorry mv is equal to h over 2 pi, this is r, and what do we get here? It is hmvr is equals to h bar. And so when we talk about when we talk about uh, this over here in terms of quantum mechanics, because when we talk about L is equal to R times P, what is P? P is nothing but mv. So this and this, these two match. So I can write the equation as L in terms of quantum mechanics or quantum physics. We take it as is equals to h bar. Now, when we are talking about the circumference, in terms of circumference over here, no matter how many times I go around the circle, I go once, I go twice, I go thrice, and I go 4 times, 5 times. So whenever I start and no matter how many circles I do, I come back to the same point. So we could write this equation over here as L is equals to number of times you go around the circle times its h, reduced Planck constant, which came from this over here, h over 2 pi, which is short form for reduced Planck's constant. There are many other ways to derive reduced Planck's constant as well. And one more thing, angular momentum is one of the quantum numbers. Okay, quantum numbers, one like principal quantum number, angular momentum is, this is one of the quantum number, then general the principal number, then what else, like spin is also one, spin is also one part of it. Yeah, I think spin is of course related to angular momentum. And one more thing, I have talked about spin in my old videos as well. In spin of quantum mechanics, the spin of quantum mechanics is very different. If I want to explain spin of quantum mechanics, I would say that particle is spinning not because of what it is, not because of what it's doing, but because of what it is. The property of spinning in a certain pattern is because it is that particle. So positive spinning in certain directions because it is a positive, and negative spinning in that electron spinning in certain way is because it is an electron. So here we're talking about the why, no, its existence is its spin, its existence is what we're talking about in my label sentences, how you would say. And so yeah, here main thing to summarize is that we talked about Planck's constant, how it's important for quantum mechanics, that it governs the laws of quantum mechanics. Wherever you will see in quantum mechanics, you will find h, and even in the Schrodinger, the famous Schrodinger equation, you will find h bar, what do you call that, h bar over here. Look at this, negative of h bar square over 2m square lambda, sorry, wavelength, plus not plus d square this over dx squared plus vx, and then we have lambda. Now look at this. Even in this we have this equation, which is, look over here, yeah, over here. So even found in even found in the Schrodinger equation. Schrodinger equation. Okay. So Schrodinger equation is what it defines particles behavior. It defines particle behavior. It's extra. You can take this as extra. It's same thing. It's related to Planck's constant, so we talk about it. Defines particles behavior, and since we know that h bar represents h and h bar, they represent the scale. So it's used every sorry everywhere in quantum mechanics.